AI is starting to separate raw capability from the labels we use to describe it. One result shows that transformer attention heads can be approximated with executable Python programs so well that you can swap out a large fraction of them with only minor degradation. Another shows those same systems can be pushed into security critical failure modes at the hardware level, from rowhammered GPU page tables to full privilege escalation. And in robotics, a similar split between how to move and what to do is unlocking strong performance with far fewer expert demonstrations. Let's explore the first paper, Explaining Attention with Program Synthesis. Explaining Attention with Program Synthesis from NJIT and MIT EECS reframes transformer interpretability as executable code search rather than natural language labeling. The authors extract attention maps from BERT-base, GPT-2, small, tiny llama-it, comma-it-bay, and llama-it-tray-bay, then use Claude Sonnet 4 to synthesize Python programs that approximate each head's behavior on tiny stories and rank them with Jensen-Shannon distance and intersection over union. The resulting library contains 1,664 programs built from fewer than 4,000 candidates at about $150 API cost. And the best fit symbolic proxies can reach up to 99% mean IOU on some heads. Across models, mean best program IOU rises with scale, reaching 69% for GPT-2, 74% for Tiny Llama 1, 1B, and 79% for Llama 3, while BERT-base is hardest to capture because bidirectional attention is less structurally constrained. The causal test is stronger than alignment alone. Replacing as many as 25% of attention heads with synthesized programs increases perplexity by only 16%, and substituting 30-40% of heads does not significantly degrade performance on HelloSwag, Pika, Psycha, ARC Easy, Social IQA, or COPA. The key result is that many attention heads are not just describable but functionally substitutable by symbolic Python programs, giving a direct path from mechanistic interpretability to model editing. Let's explore the second paper, GPub Reach Privilege Escalation Attacks on GPUs using rowhammer. GPub Reach, from the University of Toronto, shows that NVIDIA GPUs with GDDR6 memory can be pushed beyond data corruption into full privilege escalation by combining rowhammer bit flips with GPU page table tampering. The core insight is that NVIDIA's GPU page tables are stored in device memory and can be massaged into vulnerable physical locations, then corrupted, so a single flipped page frame number redirects a process's own mappings to another page table page, yielding arbitrary GPU read-write access. The authors reverse-engineered page table allocation behavior in the NVIDIA driver, finding 2 megabytes page table regions and a UVM-based allocation path that can be coerced into 64 kilobytes and 4 kilobytes pages, reducing the memory needed to fill a target 2 megabytes region from 256 gigabytes to 1 gigabyte, and enabling a timing side channel to detect new page table allocations. On an RTX 6000, they profile 34 bits flips across 6 DRAM banks and identify 9 exploitable flips for page table corruption. The online exploit reaches GPU side privilege escalation in less than 20 seconds. With that primitive, they leak CUPQC MLKEM 512 keys with 4.4% success across 1,000 key exchange runs, stealthily degrade PyTorch inference by corrupting one branch in CUBLAS, so AlexNet, VGG6, ResNet Health Threads, DenseNet Health 100 all InnoThreads, and Inception v3 all fall to 0.1%, 0.12% accuracy, and even escalate to root on the host by abusing trusted GPU-to-driver DMA paths under IOMMU protection. Let's explore the third paper, Learning to Move Before Learning to Do Task, Agnostic Pre-Training for VLAs. This Fudan University paper introduces Task-Agnostic Pre-Training, or TAP, for Vision Language Action Models by separating how to move from what to do. Instead of treating every robot trajectory as a language-labeled expert demonstration, TAP first pre-trains a Qwen2 5VL3B backbone with a SIGLIP visual encoder on cheap, unlabeled interaction data, including discarded bridge trajectories and autonomous random play, using a self-supervised inverse dynamics objective that predicts the action between two observations. The second stage then fine-tunes on a small expert set with standard behavior cloning. On the simpler benchmark, TAP, 20K reaches 33.32% AVG, all success, outperforming standard BC at 23.15% by 10% absolute, and approaching internet-scale baselines pre-trained on OpenX embodiment while using only 5K expert trajectories in Stage 2. In real-world WidowX 250S experiments with only 200 expert demonstrations, TAP is pre-trained on 30 hours of self-exploration and achieves strong robustness. Under background texture shift, it scores 25% on Put the Carrot on the Plate versus 10% for Nora. And under viewpoint variation, it still reaches 15% and 25%, where Nora collapses to 0% on both tasks. The ablation studies show that scaling stage, one exposure from 20K to 100K steps, raises AVG-all from 18% to above 30%, and GradCam visualizations confirm that inverse dynamics pre-training concentrates attention on manipulable objects before any language instruction is introduced. That's a wrap on today's AI paper highlights. Thanks for watching.